All right, welcome. And I guess I'm the last one, right? Okay, well, whatever. I still think you should go to this session. All the sessions are cool, but this is a really cool session. And I think this is largely because verified compilation is really cool, right? So at a high level, the idea is like you have a program, you want to prove stuff about it, and that's all well and good, and a bunch of you do that. But then you compile it, and it really means nothing because you compile it to x86, and this is like a nonsense architecture where you can do all kinds of crazy things. And in particular, one of the things that falls apart is like security just kind of goes out the window, right? Like all the things that we see online about people getting like popped, it's because basically we are terrible at compiling things for real. So like I think the whole kind of like general like area of verified compilation is trying to solve this problem, both for security and more generally for like actually like saying that, you know, if you run this program on your insulin pump, ideally it won't kill you, you know. So we can prove all kinds of interesting things. And this is a really, really cool area because there's lots of hard problems. And really the only thing I want to tell you about the session today is what I think are the problems in these papers. And I think that alone like is the reason why you should go there. The solutions happen to be cool, but the problem space is super duper cool, right? So when we compile things, one of the things that we have to deal with is low-level code. This is gnarly, it's gross, but it's also beautiful because it's real. The same goes with hardware, right? Hardware is really hard to actually like work with. When we like write our functional programs and want to prove things about it, we actually want to say that, you know, when you flip a bit, that actually does do what you think it does. It's also interesting because if you look at real systems, they're not written in just Haskell, sorry. They're actually written in like lots of like different languages, and like when we compile these languages, we want to mix them together, and we want to say something at the end of the day about how we mix these things, and that the verification of the whole system as a whole actually like is the thing that we want to say something about the whole system, not just about individual components. And it turns out that if you just say things about individual components, it doesn't compose super well. You have to think about the bigger picture. And it's also really fun because a bunch of time we're going to do these things at runtime, right? So we're going to do it in just-in-time compilers. The really good part about just-in-time compilers is that on a daily basis, right, all of you are using them, and they're merging untrusted code, right? So this is really fun from a compiler's problem because we're like actually just processing untrusted data. So not only do we have to get our compiler right, and meaning like we have to get it to do the right thing, we need to actually like deal with the case where the compiler itself is actually like potentially exposed to adversarial inputs. And if you're like not convinced enough, there's a whole workshop on this at the end of the week. So, you know, just that alone might tell you that this is pretty cool. Okay, so with that, I want to basically go into some of the papers that you're going to see. So I don't know what the actual order is. This is the order I read the paper. I think they're all kind of cool papers. So the Deian paper is on basically doing verified data layout refinement. So what the hell does that mean? Well, if we look at like low-level systems, and this is, you know, a piece of code of a timer driver, they're doing all kinds of super important things, but it's also super gnarly and gross code that you probably don't want to look at. You don't need to stare at this. It doesn't actually matter. The big bit is there's lots of bits, lots of macros, there's lots of shifting, and if we screw this up, your timer does the wrong thing. What we really want is to verify these low-level systems. There are many ways we can do this. The way I like to think of this is there's a spectrum of how much you're willing to sweat and how much you're willing to cheat. And kind of somewhere there, we have a pretty nice kind of balance of like verifying real things and potentially, you know, cheating about what we're actually verifying. The cogent approach, which is what Deian builds on, is basically taking a compiler-driven approach. So the idea is you write your code, so you write your driver, say, in high-level language. So nice, good, healthy, functional programming language. Then we compile it to C. This is gross, but we're going to need to do this. And then we're going to prove that the C that we actually generate actually refines the high-level code, right? So the idea is write it in the thing that you actually want to write it and compile it to the thing that you need to compile it to, and then we can prove that we did the right thing. So this is super cool because we can use, you know, real PL abstractions like ADTs, right? So like you don't have to do bit masking and all the like bit shifts. You can like actually use ADTs and modify data structures. Right? This is like what we like to do. It's also like awesome because we can write proofs just as like equations. We don't have to think about like, well, if I flip this bit and write this like gross proof that over time becomes completely like unmaintainable. The catch is, you know, we actually like have to think about like what this ultimately compiles down to. And like really, if we like want to do the thing that I just mentioned with existing systems, you kind of can't. It's kind of a lie. We want to do that, but in reality, what happens is we end up writing a bunch of glue code from your functional language to the actual thing that talks to hardware when you have to flip a bit in a particular register, right? So this is glue code. It's slow, right? We're marshalling data structures from this high-level thing to this low-level thing. It's also error-prone. because one, we're like actually baking into the compile abstractions. We have to tell like the C code like what the representation of this ADT is in memory, which means that if we want to iterate on the compiler design itself, right, like we have to now change our code that was implementing a device driver. Like that seems ridiculous. It's a total lie. And really, what this paper is about is making that thing not a lie. So it gives us the good things that we want, which is high-level programming and high-level proofs. And kind of the way it does this is effectively by extending this language with first-class layout. So you can tell it how to lay out structs in memory, and that turns out to give you basically 90% of like what you need to compile to real code. Right. So the way I like to look at this paper, it's kind of like CSS in some sense. So the way I like to say is like Dargen is to codegen like CSS is to HTML. So that's pretty cool. It's kind of natural. It's a pretty obvious idea, and it's a really cool idea. Go see the talk. I'm totally trivializing everything. Okay. The second paper is dim sum, and this paper is on basically making the multi-language verification story also real. So that's the way I like to look at all these papers. Right? So if we look at real systems like the Linux kernel, I don't know, the Wasm time compiler or GHC itself, these are many language systems. Right? We have all these languages that are combined into one big project. And this makes the whole verification story super hard. Right? So if we look at a very simple program here, written in this high-level language called rec that basically looks like ML-ish but has also C-ish like structs, all we're doing here is allocating an array, moving a few elements from the array, and then we're printing this thing out, right? So if you look at this thing, how would you actually implement this for real? Well, you might have some library called, like, let's see, a memmove, where you actually implement memmove in terms of like some lower level primitives that say like, move this part of the array to this other part. And you might have like a memcopy type thing, right? So this is standard library-like things. But if we actually look inside, well, how would you implement print? Well, at some point, print is going to have to call into the OS, right? Like there is no print in your language without calling into the OS. Now, suddenly, we're introducing a different language, right? So this language is really kind of x86 because it makes an interrupt to your OS. Your OS is the thing that knows how to print things. Your language doesn't. It's kind of a lie. And similarly, like if we look at like this library memmove, well, internally, memcopy and memmove actually end up using x86 themselves to basically efficiently copy memory. Otherwise, you're in a world where you have to do things piecemeal. Right? You could implement them in your high-level language, but that'd be super slow. Okay, so if our goal is to prove for this simple program that the program prints out 1, 2, 3, there are different ways you can do this. Most of them don't kind of like work out for like different kind of reasons. So first, you could try to lift everything to the source language. That doesn't really work because there is no syscalls at the source language. You can lower everything to source and target. Have fun proving that. That's really gross and really hard when all you try to do is print that the thing like outputs out 1, 2, and 3. Okay, so this paper actually solves this problem. And really, like if we look at like what problems that they're ultimately solving is it's making it possible for you to like write your proofs. Well, let me skip that because I don't have time. But it's basically like ultimately, if you look at those trade-offs, you end up giving up on good things. And in particular, you have to like reason at either too high of a level or too low level. And what we want is the ability to reason at each different level in its own language. So the idea is like with dim sum, you can actually do this. And it's kind of like a mix and match type approach where you're not baking in any of these assumptions. You're saying I can verify things in a high level language, I can verify things in a low level language, and then I can verify things at the interoperability level and not have to like do all this bleeding across the boundary. Okay, can I take 30 seconds for the last paper? Okay, the last one is on formally verified JITs. JITs are complicated. They're super duper buggy. They do actually get used against real people, and sometimes those people get killed, unfortunately. The reason they're really hard is because we're basically mixing runtime interpretation with runtime compilation, and then when we compile this piece of code, we now start executing this code. Rust won't solve the problem. Sorry, Rust people. There are many ways you can verify JITs. Again, it's on the sweat to cheat ratio, where like the sweat is, well, not really sweat. We have end-to-end verified JIT compilers. I would say they're toys. And on the other side, we have verified little bits of JITs. Kind of not great. Where this paper comes into play is it actually does it end-to-end for a pretty realistic JIT. So it's called FMJIT, and it stands for free monad JIT. And the idea is basically like we're going to reuse the COMSERT backend to generate verified x86 code. Then we're going to define this like small subset that we really need to implement JITs, and we're going to like write that thing in C. but have a model for it in Coq so that you can actually prove that when you generate code at runtime and when you start executing this code at runtime and when you de-optimize things at runtime, you're doing it right. And I will shut up and give you back your breath.
Thank you.